So you have your fabric resistive bend sensor or pressure sensor or your fabric switch, and you want to hook them up to a microcontroller. So I'm going to show you some ways, flexible ways of doing this. The first thing to think about is that even though that's a switch, which we usually write this way, being made of a fabric means it's probably quite resistive, and over time it will be resistive. The long cables, and also the connection here is not typically gold plated like your regular leaf switches and mechanical switches, and not designed for high current, and it may corrode over time, and so the resistance of this may go up. So we probably want to think about measuring switches as resistors, and this sensor is a variable resistive sensor. So let's just use the variable resistance symbol for that. So in either case, we usually send two wires into the microcontroller. We ground one of them, we send the other into the microcontroller, and our microcontroller often has a pull-up resistor that goes up to its power supply that we can turn on. It has a switch inside, so we can represent that switch inside for the pull-up, and we read the value in software of the voltage here, and that tells us whether the switch is closed or what value the variable resistor is. So we're going to make a slight modification of this. We're going to not ground it, but connect it to another microcontroller wire into another pin of the microcontroller, which also has a switch in it, except this time we use a microcontroller that has a pull down as well as a pull up. Pull it down to ground. And now we will measure the left value and the right value and subtract them in the software. This is called the differential approach because we're doing it with the differences. And it's a good one for a number of reasons. The first one is that if this resistance is large, these signals are going to be noisy, and this helps cancel some of the noise. And this is particularly, these large resistance values are particularly the case for stretch sensing fabrics. So that's the first advantage. The second advantage is if there's any chance that someone may come in contact with the sensor, anything over here, we don't have very high current path. So for safety reasons, because the current flowing in the system goes through these resistors, they're typically 20 to 50K, which limits the current. There's a typical strategy used for measuring a contact-based heart rate is to make sure there's a series resistor, a large value away from the electronics, keep people safe. The disadvantage of these large impedances is that there's more likely to be noise on these signals in here that the microcontroller is reading, and so we need to lower the impedance there. And the typical strategy for that is to add a buffer with an op amp in here. And send that into the A to D inputs of the microcontroller. And again, for reasons of safety and also to limit high frequency noise from cell phones and radio frequency interference, it's good practice to put a resistor in here. It also saves these inputs from high voltage spikes that might occur, and a capacitor to ground in here can be added to shunt all the high frequency energies into ground. It's a kind of low pass filter. So that is the usual differential high impedance practice for measuring sensors, and it's exactly what was implemented in this microcontroller board here. And this is the op amp. There's actually 4 of them in that package, and those series resistors are here, and the space is there to add the 4 capacitors, 1, 2, 3, 4, for the filters. And that's a question of the performance. Choosing that capacitor is a question of the performance you want to achieve. Turns out I picked an op amp that already has some high frequency, special high frequency elimination circuits, so I left it out of this particular implementation. This is designed to receive a microcontroller called the Teensy, which has the best software for what we're doing. And when they're assembled, it looks like this. And we chose a connector, a 4-pin locking orientable connector, that these special cables can be used to cable up the sensors. A further advantage of this circuit, which is arranged with the Teensy circuit, is that the microcontroller pins here and here, which were used to provide these switchable pull-ups, also go into the cap sense inputs. That's the capacitive sensing inputs of the microcontroller. This means, as well as switches and resistive sensors, we can connect up our favorite patterns for, so interdigitated capacitive sensing pattern, or simply a coil. We can build custom capacitive sensing arrays and use the same connectivity and read from the cap sense. In addition, there's an advantage to using capacitive sensing with resistive and switches. Let's say a switch develops a fault, and there are lots of kinds of faults they might develop, but one of them might be that this switch, when it gets closed, doesn't release. Maybe the fabric in a mechanical switch, there's usually a spring to throw the conductors apart once you let go, but perhaps this will wear out in the fabric and there'll be a short in here. It's possible to sort that situation out, at least identify it and know that the switch needs replacing, and in particular to not, if this was controlling a wheelchair drive or something mission critical, we would not want that switch closure to cause any danger. So what we can arrange to do is measure the capacitance as well as the closure, and only accept a closure if there clearly was a person in proximity to the switch using the capacitive measurement. It's also possible that in this long cable run here, that there's a break in the cable on either or both sides. And this can be recognized by an abrupt change in capacitance, or if there's a break on one side, the capacitance will be very different as sensed on the two sides. And that would be an indication of a cable failure. The software library associated with this allows for all this role switching between these sensors, measuring differentially, measuring capacitance, turning the pull-ups on and off, and so on. So once you're committed to the board and you've wired your sensor up, none of this electronics is your concern. It's all wrapped in the software library for the FlexAbility board. Here are some more hidden flexibilities behind this sensing arrangement that we're proposing with the FlexAbility board. I actually have two sensors in there, a resistive and a switch. It's actually possible to wire two sensors to these two wires if somewhere along the line, lines to the sensors, we incorporate some diodes in opposite directions, like that. By swapping the role of these two pins from pull up to pull down, and conversely pull down to pull up, we can arrange that the current only flows down one of the sensors at a time, and by switching back and forth we can measure two sensors on two wires. This has been generalized for LEDs where multiple wires and multiple pairs are activated at once in different directions. This is often referred to as Charlie plexing. Other possibilities of transducers that this arrangement will work with include a magnetic pickup, magnetic microphone, and the PGA, the perennial gain amplifier, can really help here because it's a low impedance transducer. At the other end we have the very high impedance capacitive transducers like condenser microphones or piezo sensors. In the case of piezos, it'd be wise to add a resistor here of the order of a megohm to establish the bias voltages at each side of the transducer. The relatively low impedances of the pull-up and pull-down will result in a low-pass response, which is probably useful anyway at the low sample rates of the microcontroller. And that will result in a smaller amplitude than one would typically see on these piezo transducers. But again, we have the perennial gain amplifier we can adjust to get the dynamic range we're looking for.